Today's video will demonstrate how to perform multiplication with floating point numbers. Hello, I'm James Helfrich. We take it for granted that our computer can multiply floating point numbers. But how exactly does that work? And especially, how does that work if we want a floating point number that does not take the standard 16, 32, or 64 bits? This video will demonstrate how to do that. Now, before we get too far into this, we need to review a little bit of math. When multiplying exponents, the exponents are added. Let's say 100 times 1,000, and that's, of course, 100,000. That's the same as 10 squared times 10 cubed, which is 10 to the fifth, which is also 100,000. Notice how the 2 and the 3 get added to the 5. This also works with binary numbers. They say 4 times 256 is 1,024, but that's 2 squared times 2 to the eighth, and that equals 2 to the 10, which is 1,024. In other words, we add the exponents of 2 and 8 to get to the 10. And this is an important part about floating point multiplication. Now, in order to multiply floating point numbers, we have a four-step process. First step is to convert the multiplier and the multiplicand into the fixed point notation. The multiplier is on the left-hand side, and the multiplicand is on the right-hand side. Then we're going to multiply the significance, then we're going to add the exponents, and then we're going to convert the result back into the floating point notation. So let's take 21.5 times 4.75. Now I want to convert them into fixed point notation where I have a whole number of significand and a whole number of exponent. So this is 1.34375 times 2 to the 4, and that's how the computer stores floating point numbers. And then 4.75 is 1.1875 times 2 squared. If you multiply that out, you get 4.75. But now we want our significand to be a whole number, and so we're going to have to move the exponent to the right. And that's the same as 43 times 2 to the negative 1, and then 19 times 2 to the negative 2. Once we have those, then we're going to bring the significand over to the left-hand side and the exponent to the right-hand side. And then we're going to multiply the significand, and then we're going to add the exponent. And when I finish with this, I have the product. And the final step is to convert this back into floating point notation, which is 1.595703152 times 2 to the 6. And that, if you multiply it out, is 102.125, which, if you can check with the calculator, is the same as 21.5 times 4.75. Okay, let's take a look at this one step at a time here. Step number one, I want to have a whole number exponent and a whole number significant. Okay, and I have a function called get significand and get exponent, which does this for me. So let's take 21.5 times 4.75. So my multiplier is 21.5 base 10, which in binary is 0, which is my sign, 10011, which is my exponent in my exponent bias format, and my significant has an implied 1 dot, and then 01011, and so on. And that equals 1.34375 times 2 to the fourth. And my multiplicand is 4.75, which has, once again, a 0 for my sign, which is positive, and 10001, which is my exponent in exponent bias format, and my significant has the applied 1 dot, and then 0011. So first we'll find my significant, which is 43, and then we'll find my exponent, which is negative 1. Now let's verify that. 43 times 2 to the negative 1 is 43 divided by 2, which is 21.5, so it is correct. Now we're going to find the significant in the multiplicand, which is 19, and then my exponent in the multiplicand is negative 2, and we'll verify that one too. 19 times 2 to the negative 2 is 19 divided by 4, which is in fact 4.75. So now I have the whole number version of the significand and the exponent. The next step is to multiply my significands. Now notice both my multiplier and multiplicand are integers. And since I can perform multiplication with an arbitrary number of bits, this should work just fine. So my significant product is my significant multiplier times significant multiplicand. And once again, I have 21.5 times 4.75, which is 43 times 2 to the negative 1 times 19 times 2 to the negative 2. Now I'm working on just significance, which is 43 and 19, right? So my significant multiplier is 43, significant multiplicand is 19, multiply them together, and I get 817. The next step is to add the exponents. Remember, my exponents are integers. So once again, I have 43 times 2 to the negative 1 times 19 times 2 to the negative 2. And my exponent product will be exponent multiplier plus exponent multiplicand. So my exponent multiplier is negative 1, exponent multiplicand is negative 2, and then when I add them together, I get negative 3. The final step is to canonicalize this. Take my integer exponent and my integer significand and turn it into the IEEE format for floating point numbers. And this is going to involve moving the decimal point to the one to the right of the most significant bit on the significand. And I have a function to do this. So my product is significant product, comma, exponent product. So once again, I have 817 times 2 to the negative 3, okay? And we want to turn it into 1.5957033125 times 2 to the 6. Let's see how this works. So my significant and my exponent are going to be 817 and negative 3, but now I got to move the decimal point over. So I'm going to divide the significant by 2 and then add 1 to the exponent. And again, and again, and again, and again. I'm going to continue this process until the significant is greater than 1 and less than 2. And there we are, greater than 1, less than 2. Now I take that significant and I turn it into the binary format, and I take the exponent and I turn it to the exponent bias format. So 0 for my sign because it's positive, and then my exponent bias format of 6 is 1, 0, 1, 0, 1, and my significant is 1 point, and those are hidden, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0. So let's verify this is true. So my exponent bias is 1, 0, 1, 0, 1. So the rightmost 1 corresponds to 1, and then the 0 corresponds to 2, and then the 1 corresponds to 4, and the 0 corresponds to 8, and the 1 corresponds to 16. So 16 plus 4 plus 1 is 21. 21 minus my bias, and my bias is 2 to the exponent 5 bits wide, minus 1 is 4, 2 to the 4 is 16, minus 1 is 15. 21 minus 15 equals 6. And that is, in fact, my exponent. Now let's verify the significant. Remember, I have a hidden 1 dot, so it's 1 plus, and then the leftmost 1 corresponds to 0.5, the next one 0.25, the next one 0.0125, the next one 0.0625, the next one 0.03125, and so on and so on. Add that all up and I get 1.595703125. And that number times 2 to the 6 does in fact equal 102.125. Okay, let's take a look at another example. I want to multiply 19.5 times 5.875, where my exponent is 5 and my significand is 10. And once again, this is the standard 16-bit floating point number. We could do this with an arbitrary number of bits, where we're going to stick with 16-bit floating point numbers for now, because it's big enough that we can demonstrate these principles, but not so big that the math becomes too difficult. Okay, so we have 19.5 base 10 and 5.875 base 10. And then the binary version is 0 for the sign, 1, 0, 0, 1, 1, which is my exponent bias, and 0, 0, 1, 1, 1, and then rest zeros for 19.5. And you can see the same for 5.875. And this is 2 to the 4. So I take 1, 0, 0, 1, 1 exponent bias format, and I find the exponent, which is 4. So it's 2 to the 4 times 1 dot, because there's always a 1 dot implied with a significant, 0, 0, 1, 1, 1. And we'll do the same thing for the 5.875. Now you can multiply these out to convince yourself that these are in fact the correct representation. Now from here, I want to find the whole number version of the exponent and the whole number version of the significant. And I'm going to do this by moving the decimal point of the significant to the right of the least significant 1. So in the first case, for the 19.5 case, I have to move it over 1, 2, 3, 4, 5 slots. And as I move the decimal point to the right by 5 slots, I got to subtract 5 from the exponent. So now my new exponent is -1, and my significant is 0, 1, 0, 0, 1, 1, 1. Now we'll do the same thing for the 5.875. I got to move the decimal point to the right 1, 2, 3, 4, 5 slots. When I move it 5 slots to the right, I got to subtract 5 from the exponent, so it becomes exponent is -3, and my significant is 0, 1, 0, 1, 1, 1, 1. So the whole number version is -1 for my exponent, and significant is 39. And once again, if you take 39 divided by 2, which is 2 to the -1, then we get 19.5. And then for 5.875, that's 47 times 2 to the -3, which is 47 divided by 8, which is in fact 5.875. So we can represent these numbers as 39 times 10 to the negative 1 times 47 times 10 to the negative 3. Using the commutative property of addition, I will move the significance over to the left and the exponents to the right. I will multiply the significance and I will add the exponents. And from here, I got to canonicalize it by moving the decimal point back over to the left. So 1,833 becomes 1.7900390625 times 10 to the negative 6. So I had to move the exponent to the left by 10 slots. From here, I have to convert it to binary, which becomes 0 for my sign, 10101, which is 2 to the 6 in the exponent bias format. And then, don't forget the implied 1 dot, 1100101001. And that equals 114.5625. And we can verify that's true by saying 19.5 times 5.875, and that should equal 114.5625. Okay, try this yourself. See if you can find the product of these two 16-bit floating point numbers. You can learn more about multiplication of floating point numbers in the multiply section of the floating point chapter of the C++ data structures textbook.